Okay, we'll now do some exercises. Okay, the first one, Hahn-Banach extension is not unique. In particular, x naught not equal to 0 implies there exists f in V star, norm f equal to 1, f of x naught equals norm x naught is not unique. So let us give an example. So let us take R2 with the L infinity norm. So let us take L to infinity. So this is R2 with the norm infinity. And let us take x naught equals 1 1, and let us take f of xy equal to x and g of xy equal to y. Then any linear functional is continuous in finite dimensions, so fg belong to L2 infinity star, and then it is very easy to check that norm f equals norm g equal to 1, because mod fxy is mod x, mod gxy is mod y, both of them are less than norm xy infinity. And then you take 1 0 or 0 1 as a test vector, then you will get that the maximum is achieved. So norm f equals norm g equals 1, and you have f of x naught equals g of x naught equal to so x naught equals 1, yeah, equals 1, and that is equal to norm of x naught infinity. And therefore this is not unique. So now when can we say something is unique? So that is the next exercise. So we say V norm linear space strictly convex if norm f equal to norm g not equal to 0, of course, implies norm of f plus g by 2 is strictly less than norm f equal to norm g. So then here is the exercise. So V star strictly convex implies Hahn-Banach extension is unique. So let W be a subspace. And let F belong to W star. Assume we have two extensions. Assume two Hahn-Banach extensions, G and H. So you have G restricted to W equals H restricted to W equals F, and norm G equals norm H equals norm F. So these are the two Hahn-Banach extensions we have. Then you look at norm of f plus g by 2. This is of course less than or equal to 1/2 of norm not f plus g, g plus h. Norm g plus norm h. Each is equal to norm f, so this is equal to norm f. On the other hand, g plus h by 2 restricted to w equals Since both of them are equal to f, this is equal to f, and therefore norm of g plus h by 2 should be greater than or equal to norm f, because it's an extension. So when you take suprema, you are taking over bigger sets, so an extension always helps bigger norm. So therefore norm of g plus h by 2 is under Hahn-Banach extension, it's equal to norm f, which is equal to norm g equals norm h, and that contradicts the fact that V star is strictly convex. Therefore you have the Hahn-Banach theorem extension is unique. Third exercise is another proof of a theorem which we, a corollary which we already did. So let us take W subspace of norm linear space V, and W closure is not equal to V. Then there exists a f in V star such that f is not equal to 0 and f restricted to W is identically 0. So this is what we said is the way of proving subspaces are dense. So we used to prove this using the fact that you had the separation of convex sets. Now we want to do it using the extension method. So let x naught belong to V minus W bar. So then W closure is closed subspace, and therefore you can consider V by W bar. So this quotient space is well defined, and then you have x naught plus W closure is not equal to 0, because x naught is not in W bar. This coset cannot be the 0 element. So by Hahn-Banach, or the corollary which in fact we started with, there exists a phi belong to V by W bar star such that phi of x naught plus W bar is in fact equal to norm of x naught plus W bar, and that's not equal to 0, and norm of phi equal to 1. So now you define f from V to R. So f of x naught is nothing but phi of x naught plus W bar. So we just go to the quotient space and then compose it. So f of x naught, sorry, this is true for all x. So we are going to define this for all x. So in particular, f of x naught equals phi of x naught plus W closure, and that's not equal to 0, we just saw. So f is not 0. So is it a continuous? What about mod fx? This is equal to phi of mod of phi of x naught plus W bar, and that is less than or equal to norm phi, which is equal to 1 of course, into norm of x naught plus W bar. But what is norm of x naught plus W bar? Is the infimum of all norm of x naught plus W in W bar. In particular 0 is there, so this is less than or equal to norm of x plus W bar. This is not x naught, sorry, I always get. Therefore f is continuous, so implies f belongs to V star. And finally, if W is in W, we have f of W equals phi of W plus W bar, but this is the 0 element in the quotient space, and therefore phi of 0, and that is 0. Therefore f restricted to W is identically 0. So this proves the version using the next exercise. V non-linear space and W contained in V subspace, and X is a finite dimensional non-linear space. T from W to X continuous. Then there exists T bar from V to X continuous, linear, continuous linear of course, and T bar restricted to W is nothing but T. So previously we extended linear functionals in the Hahn-Banach theorem. Now we are trying to extend linear operators, but in the case where the range space is finite dimensional. Okay. So solution, you take a base, this is just, you have to apply the Hahn-Banach repeatedly. So E1 En basis for X. So you can take any x in X and you can write the X equals sigma xi in R. Okay. So now you define Pi of X is the projection, namely xi. Then this is a continuous linear functional. It's immediate to see. In fact, if you are finite dimensional, everything is continuous. Every linear map is continuous. So this implies Pi composed with T is from W to R is a continuous linear functional. So there exists Ti bar or Ti, let's say I don't need a bar here. So Ti from V to R Hahn-Banach extension of PIT. So now you define T bar of X equals sigma Ti of X times EI. Then of course T bar is continuous linear, and if you have X in W, you have T bar of X equals sigma I equals 1 to n Ti of X EI, and that is equal to sigma I equals 1 to n Pi of Tx EI, and that's precisely Tx. That's the definition of Tx. Okay, so this proves this. So as a corollary of this is the next exercise. V non-linear space, W contained in V finite dimensional, then there exists a Z subspace which is closed such that V equals W direct sum Z. Now W is finite dimensional, so it's already closed. Now given any subspace in linear algebra, you know we can extend the basis and therefore write V as a direct sum of W plus Z. But we are asking something more here. We want Z to be also closed. Now this is a non-trivial problem generally, and so given a closed subspace, can you find another closed subspace such that the direct sum of these two is in fact the whole space? So this is a very important question often asked in functional analysis. We are answering it partially here, namely if W is finite dimensional, then we say that in fact there is always a complement available. Okay, so So how do we do that? So solution. So take identity map from W to W. So this is continuous linear. And W is finite dimensional. And therefore, by exercise 4, there exists a P from V to W such that P restricted to W is identity. So P is, and of course P is continuous linear. So now you define Z, you set of all x such that Px equal to 0. So this implies that Z is closed, no problem about that. It's a 0 set of a continuous linear functional, and therefore it is. What about W intersection Z? Suppose x belongs to W intersection Z, then you have that Px equal to x, and you also have that Px, because it's in Z, is equal to 0. So this implies that x equals 0. Therefore W intersection Z is just a singleton 0. Now you take any x in V and look at x minus Px. Recall that this belongs to W. So if I apply P of this is equal to Px minus P of Px, but Px is in W, P is the identity, and therefore again you get Px, and that is 0. So x minus Px belongs to Z. Therefore V can be written as range of P, which is W, plus Z, and since they are disjoint in this sense, so you can write that it's equal to the direct sum. Okay. 6. Next exercise. Every finite dimensional space is reflexive. So if V is finite dimensional, then V, dimension of V equals dimension of V star equals dimension of V double star, and so on. Now J, the canonical mapping, so Jx, so x in V, Jx acting on F is f of x. This is the mapping J. So J is the mapping, goes from V to V double star, is an isometry. This is what we saw, that is J is 1 1 also. Okay, therefore 1 1 and they are the same dimension implies J is on 2, since the dimensions are the same, and therefore we have V is reflexive. So every finite dimensional space is automatically reflexive. So this next exercise I already mentioned, so let me do it. So show that C0 star is L1. So we do it exactly as we did the L1 star is LP and so on. So you take any y in L1, so y equals y1 etc, yi, and then you define Fy of x is equal to sigma xi yi, I equals 1 to infinity. So x is in C0, which is of course a subset of L infinity. So by the Helder inequality, or even otherwise trivially, mod Fy of x is less or equal to maximum of all the xi, so norm x infinity into sigma mod yi, and that's equal to norm x infinity norm y in L1, and therefore Fy belongs to C0 star, and norm of Fy is less than or equal to norm y1. Now let phi belong to C0 star. We want to show that every element in C0 star occurs in this way, and you take Ei to be this standard sequence, 1 in the ith place, 0 elsewhere, and then you take Yi is phi acting on Yeah. So this belongs to C0 because you have only zeros after some time, and therefore this is in C0. Okay. So now you fix a positive integer k, and you define x k, its ith component, will be 0 if yi equal to 0, 1 less than equal to I less than equal to k. 0 if I is bigger than k, and yi by mod yi if yi is not 0, 1 less than equal to I less than equal to k. Then of course xk, it's just a finite thing, and therefore automatically it belongs to C0, it converges to 0, and phi of xk is nothing but sigma mod yi I equals 1 to k, because if you multiply you get yi is mod yi square divided by mod yi gives you just mod yi, and norm of xk infinity is 1. Therefore sigma I equals 1 to k mod yi is less than or equal to norm phi times norm xk, and that's equal to norm phi. So this is true for all k, and therefore this implies that y equals y1, yi, etc. belongs to L1, and norm y in L1 is less than or equal to norm phi. So now let x belong to C0. Now you define x k with a bracket below as nothing but just a truncated sequence xk 0 0 and so on. So this also belongs to C0. Okay, and norm of x minus xk infinity is equal to max mod xi I bigger than k, and that goes to 0 since x belongs to C0. So it can be made as small as. This is exactly the place where L infinity star equals L1 does not work, because if you do this truncation, this won't go to 0. That is the problem. Okay, so that is why that proof would not have worked. Okay, and therefore you have that phi of x equals limit phi of xk equals sigma I equals 1 to infinity xi yi, and that is nothing but fy times x. Therefore norm y1 is less than or equal to norm phi, which is norm fy, so phi equals fy, and norm fy we saw was already always less than norm y1, and therefore norm phi equal to norm y1. So it's an isometric isomorphism, y going to fy, so y going to fy is an isometric isomorphism from L1 to C0 star, and therefore C0 star can be identified with L1.